Okay, let's start today's webinar. Hello, everyone. My name is Jess from MIDAS IT headquarters. So today's webinar is for the advanced course. So this is the topic of the today's session: construction of segmental tunnel lining with the 3D modeling. And this example demonstrates the 3D simulation of the construction of a segmental tunnel lining. The tunnel consists of, in this case, a number of 10 links with the 6 different segments each. For the placement of each link, the slice of soil is excavated and the link with segment is installed simultaneously. And the line shell interface with the Janssen model are available for the bending stiffness of joint between the segments. So in this example, we will use simply one soil layers, which is used by the more general models. And you can see that the input parameter in this slide, of course, we'll start this model by using the start file, which already predefined these input parameters, especially for the material property. And about the structure part segment, we'll use the simple elastic material model with the elastic modulus Poisson ratio and the shell type of element with the thickness of the 20 centimeter. And finally, lastly, we will insert the shell interface between the shell segment. So it consists of the two different stiffness modulus with the normal direction and the shear direction. Okay, then. So let's move to the GTS NX program. So as I mentioned, I opened the start files. Again, we have the material for the soil ground with the general Mokulon model and the sum of the strength, cohesion, and the friction angle with the last tension cutoff, and the segment by using the elastic material model, and the segment connections here. So in the beginning, as I mentioned, that we can consider the nonlinear elastic behavior by using the Janssen theory, and also you can consider the Coulomb friction. But by using this option, that sometimes it takes a little bit much time to converge the stages. So in this example, I will skip this nonlinear property options. And the section property here, as I mentioned, that the 20 centimeter of thickness will be used for the segment lining. And again, for the segment connection thickness, same with the that of the segment lining. So firstly, let's create a tunnel section considering the 6 segment. So for this, we have to change some options. So here on the main menu tools, and here is the option. And in these options, the second geometry tab, you can change the split revolved case. By default, we use the 90 degree. But in this case, as I mentioned, that we are considering the number of 6 segments for each links. That let's change the value with the 60 degree, and then click OK. Then next, let's create a simple circle by using the geometric functions. So on the geometry, here point and curve, and here is circle. So we provide the different type of method, depends on your case. So in this case, let me use the first method. So firstly, you can input the center location, and then click enter. Then it is ready to enter the radius. So I will use the 4 meter radius, and then please use the option make face and click OK. Then you will see that the circle has been generated with the diameter 8 meter as we have input. And the next, by using this circular surface, we will create the slice for the tunnel excavation. So in this case, I'll use the protrude function on the geometry. Here, protrude and extrude. So select the circle face and then direction. Please use the Y global axis, and the length means for the excavation length. So 1.5 meter, and then click OK. So now we have the one solid with the type shape of cylinder, and by using this solid, we will transform and translate. So again, please select the solid slice, and then with the same directions, select. Then please use the copy uniform. So with the same distance, 1.5 meter, and then 9 slice should be copied. And now we have the totally 10 slice of the excavation. Okay, then let's move the next. So let me briefly explain about the modeling the connection between the lining segment. So as you know that many tunnel linings are jointed. So this introduces a particular modeling requirement. So probably the simplest way to model these tunnel linings is to use the shear element and leave a gap at the position of the joint between lining segments. And the tight freedom boundary conditions can be applied between the two nodes representing the end of the adjacent segment. So here in this left figure, you will see that between node A and B, the two nodes can be tied so that their displacement are the same, but their rotations left untied. This will result in a joint that is free to rotate, which is cannot sustain a moment, but will be able to transmit axial thrust and shear force. Clearly, this is a simplification, as most segment linings will be able to transmit some moments across their joint. In case of the plane strain analysis, which means that 2D analysis, The idealization represents a tunnel with the unknown linings, as shown in the right figure A. But as you know that in reality, the lining segments are rolled in figure B, and the above model in figure A may not be appropriate. So this is the reason why we have to do the 3D analysis in case of the TBM. Okay, then let me forward. So this step, let's rotate, slice, and create model boundaries. So in this case, we have the unrolled shape of the tunnel linings. So by using the rotate function on the geometry, transform and rotate. Then from here, please select the second, fourth, sixth, eighth, and the last slice. Then rotation axis with the Y global, and select move with angle 30 degree. So after that, you will see that unrolled lining has been moved. And next, let me create the solid box for the ground boundary. The geometry, here is the box. So the origin point minus 20, comma 0, comma minus 20. And the width 40 meter. The length 15 meter. With consist of the number of 10 excavation for each 1.5 meter, and the height 40 meter same. So now we have the boundary box. And the next step, we have to divide the excavation part with the solid box. So for this, simply you can create automatically shared space between the tunnel excavation and ground by using the auto connect function. So under geometry, so here we have the box without the excavation part. So on the geometry, here is auto connect, and select all the geometry and click OK. So now we have the box without the excavation part by using the auto connect functions. So for sure, to check the shared space after creating 3D geometric object, precase would be created when mesh set are generated on shared solid, and it will cause the inaccurate analysis result. So on the geometry, we have the check duplicate. So here, please click, then you will see that the shared space will be seen with the orange color. So before auto connect, as you can see, there is no shared space. After auto connect, so we see that shared space like this. So this is very important step before the mesh generation. Okay, then next, let's generate the meshing for the tunnel excavation and the ground. So This is the end of the geometry creation. So now we will generate the meshing. So firstly, let's create the meshing for the tunnel excavation. On the meshing 3D here, then select the 10 solid with the size 1 meter and property soil, and mesh set slice, and click apply. And then next, let's create the geometry meshing for the ground box. So select the ground box, and for this, let's use the size 5 meter and the name ground. Okay. Okay, and let's go to the next. So in this step, we will generate the meshing for lining segment. So since we already create the meshing for the tunnel excavation by using the solid slice, we will use the extract function, which can be create the 2D shell element from the geometry solid. So firstly, hide all mesh, and then show the excavation solid. And on the meshing element, here is the extract. So please select the type paste, and then select the paste, 6 paste for each slice. So by using, you can drag the mouse, and with Control key, you can select all objects that are crossed by the selection rectangle. This is the crossing selection. So please keep in mind, you have to use the Control key, or here is the icon, the intersect selection, which is the crossing selection. And the 6 face has been selected. And then check on the register based on object shape to create the different 6 segment mesh set. And then the name ring 1 segment, and click apply. So similarly, please do the same for other slides. Select second, link 2, and the third, fourth, and fifth, and the next. And seventh, and the last. So then let me hide the solid geometry. So as you can see that the segment lining mesh set has been created by using the shell element. And then since we have selected the option, the register based on the object shape, then you can see that each different mesh set for the segment, which is consists of 6 different segments, has been created with the different mesh set. Okay, and let's move next. So now let me briefly introduce about the shell interface element. So in MIDAS GTS NX, the shell interface element is primarily aimed at modeling the nonlinear behavior at the joint of prefabricated lining segment. This is particularly relevant for TBM modeling, you know. Joints between segments are the weak points of TBM linings, and the concentrate translational and rotational deformations are among the main factors which should be considered. Inserting shell interface elements between plate elements that is used for modeling the lining segments allow capturing these concentrate translations and rotational deformations. The shape and the formulation of shell interface element is similar to standard line interface element. However, rotational degrees of freedom are added to each node to ensure full compatibility with adjust plate element. In GTS NX, the constitutive behavior available for shell interface elements include the Coulomb friction for sliding displacement and Jansen's law for hinged rotations. So some other software, they can only consider the joint by using to control the constraint, which is the hinged or something like that. But in GTS, you can consider this behavior of the shell interface to simulate the joint connection between the shell segment, between the segment radial direction, and between the ring and between the segment. You can control more accurate behavior by using this shell interface element in GTS NX. So this is one example of using the shell interface element. So as you can see, it consists of the different mesh set to simulate the several segments between the segment and between the ring. Actually, the line interface, shell interface, has been created with the line shape, and then after analysis, you can check the deformation and the moment result between the segment like this. So in this step, let's create a line interface between segments and rings. So here, on the mesh, here is the element, and here is interface. So we have the three different tabs. First line is to create the general interface in 2D modeling. For example, the excavation case between the wall and the ground. And the last one, plane type. This is again the general interface in case of 3D modeling. And the middle one is the shell interface. Now we are using these functions for the lining segment connection. So on the shell tab here, let's select the type from mesh set with the TX cross type. So because that the mesh set has been crossed with the T shape, and then select all mesh set, and property segment connection. So the name, segment connection 1. So click OK. So now you will see that the line segment connection for the shell interface has been created. And another step we have to do is that to create the line, after create the line interface, then we have to assign the different mesh set because to consider the stage of construction, each part of the shell interface should be activated. For this, we have to divide this mesh set with the different stage of the construction. So for this, firstly, let's create the new mesh set. With a different number of the stages. So, and then let's have change the name. So now we have the segment connection 1, 2, 3. Sorry. Change the name and enter. Again, you can change the name by clicking the keyboard F2 and Ctrl C, Ctrl V. You can use of course. So after that, so actually now only in the mesh set segment connection 1 has all the shell interface. So in order to include the mesh set in the different mesh set, for example, segment connection 2 and 3 like this. So again, right click, and here is the include exclude element and node. So with the side view here, let's select this part and this. So this part, I will include the segment connection 2 by considering the stage of construction. So click apply. So similarly, you can do the same for the other mesh set. The next. And segment 6, connection 6. And connection 8. And connection 9. And lastly, connection 10. So now I have include the different shell interface mesh set considering the stage of construction. Okay, let's forward next. So next step, let's change the name of mesh set to consider the construction sequence for the tunnel excavation. So this means that we have the slice mesh set. So, but even though the mesh set name has been assigned automatically, but you can see that the order is not correct. So to consider the construction stages, start from the front and excavation. Let's change the mesh set name. So on the mesh, and here is the mesh set and rename. So here, please select the all mesh set and then slice and the starting number from 1, and by considering the coordinate or the x, y, z. In this case, particularly the y coordinate, y axis will be considered. Then click OK. Then you will see that the order has been so here is the slice 2, 3, 4, 5, 6, 7, 8, 9, 10. So the order has been aligned. Okay, then let's move forward. So this is the end of mesh generations. Now we are ready to create the load and boundary condition and the stage of construction. So show all the mesh set, and then firstly let's assign the constraint. So on the static analysis, here is the boundary and constraint. So in the last auto tab, let's select the auto tab and then click OK. So for this, let me change the name of the with the ground fixity. Okay. Next step, the self weight here. So some name with self weight. And again, the direction of the gravity will be considered automatically with the factor value, factor -1. Okay. And in this case, we need the special boundary conditions. So which is to assign the boundary conditions to simulate the effect of support by the tunnel boring machines, which means that during the TBM construction, that the tunnel head will be support for the tunnel space. So to simulate, simply simulate these conditions, that let me create the additional boundary conditions about for the effect of the support by the TBM machine. So under static analysis boundary, again the constraint. So please hide all mesh set in order to create the boundary condition by using the geometric face. So here again we have the tunnel slice, excavation slice, and then so let's hide the first slice because we need this boundary condition from the second excavation. So here, second advanced step, select type is face, and select the front face of each slice, and then DOF type is the TY, since this is the normal direction with the global Y axis. And the boundary condition name, so let's use BC2 by referring to the tunnel slice respectively, and click apply. So like this, you can do the same for other slice. So select the front face TY, and here is the BC3. Apply. Next, BC4. Apply. 5. The 6. The 7. Next, 8. The 9. And the last. Okay. So for your information that we are using this slice solid for the generation of the tunnel excavation mesh set. So any load and boundary condition can be assigned both geometry and or a mesh set directly. So in this case, to select the surface, each surface easily, I use the solid face to define the boundary condition. Okay, now we are ready to create the stage of construction. So let's show the mesh set again. And then let's define construction stage of the tunnel lining segment. So under static analysis and stage set, here add to generate the boundary conditions. So let's change the show data activate. So in the initial phase, the ground mesh set and the slice should be activate, and boundary condition, ground fixity, and the self weight. And please check on the reset displacement and click save. And next, so this is the excavation 1. So in here, we need to activate the link segment and the excavation slice 1 and the boundary condition 2nd to support the tunnel heading, and click save. So similarly, the excavation process, as you know, that firstly the excavation slice by deactivate the slice mesh set, and then install the ring segment for the second part, and then now we have to activate the segment connection 1. Sorry, but I have to assign the segment connection 1 in the previous stage. So the segment connection 1 here, and the second excavation active link segment with the segment connection 2. So this process will be continue until the last excavation. Again, deactivate the slice for the excavation and activate the segment link and or with the segment joint, and find lastly the boundary condition to support the tunnel heading. So to save the time, so I will use the final model of this. So here, so let me check the process on the mesh set, just hiding the ground. So to simulate the stage phase of construction, so the first excavation, so again deactivate the slice and activate the link segment with the segment connection and the boundary condition. The excavation second, next excavation, so and the last one. So okay, and the next we have to create the analysis case. So of course I have create the analysis case here. So lining segment in the by selecting the construction stage type, and then choose the initial stage for the stress analysis with the K-NAC condition. So and then now we are ready to calculate analysis. Actually, in this model, it takes around a few minutes. So by using my laptop, so let me check the ARF file here. So in ARF file, so you can see that this is a kind of text file. Then after analysis, you can check this text file, the result of the convergence. So and the last line. So you can see that the total calculation time. So it takes around 1 minute 30 seconds. So and considering the number of stages with the 11 stages, including the initial phase, and the final number of elements and node, you can check by selecting the all mesh set. So you can see in the property window, so node number is the around the 2,800, because the number of nodes are related to the number of the matrix equations with the degree of freedom. So let's directly check the result here. So firstly, please check the displacement of ground. So similarly in the previous page course, so you can move to the last result tab, and let's check the last stages. Total displacement with the smooth change and the deformation undeformed. So this is the total displacement, and the TX is the horizontal, and the TG is the vertical displacement. And next, let's check in detail of this 3D modeling. In case of 3D, sometimes we need to check the result of inside of the 3D geometry. So for this condition in GTS NX, we provide the different type of the functions in the post-processing. So here the toolbar, the one is that clipping plane. So as you can see that you can cut some part of the model based on the each direction X, Y, Z. So for example, if you have the name with X direction and click add, now Y direction and the G direction. So of course, you can change the section by mouse dragging, and or you can directly input the distance in here. So again, X direction as well, and the Z direction. So if you click add and close, then here we have another several options to show that only the section display and the intersection union. So and check off, then you can control these selected sections as well. So as I mentioned that to check the result inside of the model, so click plane is useful in 3D analysis. And again here we have the proof. So if you want to check the sum of the result on the inside of the model here, you can simply click the mouse like this, and we have the maximum, minimum, or absolute maximum here. So for example, if you it is critical to have to check the settlement displacement of from the crown, tunnel crown. So by using the proof functions, then you can click this node here, and then changing the unit from the meter to millimeter. You can directly show that the different unit value. On the right bottom, we have the unit length. Now I have changed to millimeter. So this one is the value for the crown, tunnel crown displacement, actually the settlement. And next, let's check some of the member ports of the tunnel lining in the circumferential direction. So release the clipping, then on the mesh post-processing workstream, we have the shell interface ports here. So here is the membrane ports access, and please hide the no result. Please select the exclude, then the ground mesh geometry will be hidden. So this is the membrane pores, which is the actual pores of the shell. But in case of the by using the tetrahedral element, and the plate element will be used by the triangle element. So in this case, we will have the different local coordinate system, which means that showing only the link segment. And then here we have the coordinate system, show element coordinate system, but as you can see that the coordinate system is not aligned. So for this, in order to align the coordinate system, so in the property window here, we have the type of the general, and here is our coordinate system. The default one is using the element coordinate system, but you can change to the global coordinate system, and then click apply. Then you can see that the coordinate has been aligned. So this one is the coordinate. Even though we have the different coordinate system from the element axis, but you can change the global coordinate system to align, and the contour plot will be changed accordingly. So default and the global. So for the design, you can show this align of the coordinate system by using the global coordinate system in the output property window, in case of using the triangle shape of element for the plate element. So this is the actual process of the plate, and the bending moment. Here we have the bending moment XX. And the next, let's check the interface result. In this model, we inserted the segment joint by using the shell interface. So we show all the mesh set and the result here on the shell interface false. So this is the normal result, which is the out of plane shear force. And here we have the rotation Y. It is actually the bending moment in the joint between the segment and between the rings. So this is the rotation Y is for the bending moment of the joint connection, and the normal X, you can check the out of plane shear force. So this is the end of my presentation. So about the Q&A. So some of the questions arise in the question chat window. So I will cover some of them. So the first question is regarding the yeah, in the tunnel construction, for example, by using the jacking method or TBM under the height way, is there a displacement requirement that occurs in accordance with the decrease in the permit space on the class of the load above? If any, are there any rules? So for this, I'd like to recommend to you for finding some of the reference in the Googling. And another thing is that to simulate the TBM construction, we have, of course, that the contraction to simulate the volume loss. So, but in this example, I have skipped using these functions because I'm focused on the usage of the shell interface connections between the segment lining. So on the static analysis, here load, this one is contraction. So it consists of two different tabs. The first shell is for the 2D TBM modeling. The beam. By using the beam tab is for the 2D TBM modeling, and the first shell tab is for the 3D TBM modeling. So in this case of the 3D TBM, then you can use this shell on the shell tab by inputting the value of the contraction and so on. Okay, then let me reply the other question that has been arised in the chat window after the session.